Consider two lines L1 and L2 in space. Let L1 be represented by equation 1 as shown. This implies that line L1 passes through a point, say P, with position vector A1 and is parallel to vector B1. Similarly, let line L2 be represented by equation 2 as shown. This implies that line L2 passes through a point, say Q, with position vector A2 and is parallel to vector B2. This further implies that vector PQ is equal to position vector A2 of point Q minus position vector A1 of point P. Let this be equation 3. If the given lines L1 and L2 lie in the same plane, then the cross product of vectors B1 and B2 will be a vector n, which will be perpendicular to the plane and vector PQ. This leads us to the condition for coplanarity of lines, which states that the given lines L1 and L2 are coplanar if and only if vector PQ is perpendicular to the cross product of vectors B1 and B2. We know that the dot product of perpendicular vectors is 0. Hence, the dot product of vector PQ and the cross product of vectors B1 and B2 is 0. Let this be equation 4. Substituting the value of vector PQ from equation 3 in equation 4, we get equation 5, which states the condition for the coplanarity of lines L1 and L2 given in vector form. Now, let us derive the condition for the coplanarity of lines L1 and L2 in Cartesian form. Let the coordinates of points P and Q be as shown. Thus, we can write vector PQ as shown. Let the direction ratios of vectors B1 and B2 be given. Using the given direction ratios, we can write vectors B1 and B2 as shown, substituting the values of vector PQ and vectors B1 and B2 in equation 5. We get equation 6. Converting equation 6 into a determinant as shown, we get the condition for the coplanarity of lines L1 and L2 in Cartesian form as shown. Consider two planes pi1 and pi2 as shown. Let the normal forms of the equations of planes pi1 and pi2 be as shown. Vectors n1 and n2 in the equations of the planes are normals to the planes pi1 and pi2, respectively. The angle between two planes pi1 and pi2 is defined as the angle between their normals n1 and n2. The acute angle between the normals is represented by theta and is taken as the angle between the planes. We already know that the scalar of dot product of vectors n1 and n2 with angle theta between them is equal to the product of the magnitudes of vectors n1 and n2 and the cosine of angle theta. Rearranging the terms of this equation, we get the cosine of angle theta between planes pi1 and pi2 with normals n1 and n2 as shown. If planes pi1 and pi2 are perpendicular to each other, then cos theta becomes 0. Substituting this value in equation 1, we find that the two given planes are perpendicular if the dot product of their normal vectors n1 and n2 is 0. If planes pi1 and pi2 are parallel to each other, then cos theta becomes 1. Substituting this value in equation 1, we find that the two given planes are parallel if the dot product of their normal vectors n1 and n2 is equal to the product of their magnitudes. Now, consider the Cartesian equations of planes pi1 and pi2 as shown. The angle theta between planes pi1 and pi2 in this case is given by equation 2. Note that here A1, B1, C1 and A2, B2, C2 are the direction ratios of the normals to planes pi1 and pi2 respectively. If planes pi1 and pi2 are perpendicular to each other, then cos theta becomes 0. Substituting this value in equation 2, we get the condition to verify if the given two planes are perpendicular. If planes pi1 and pi2 are parallel to each other, then cos theta becomes 1. Substituting this value in equation 2 and simplifying, we get the condition for two planes to be parallel.